Hey everyone, and welcome. Have you ever stopped to think about what a killer guitar solo and a simple ripple in a pond actually have in common? Well, the answer is this incredible, invisible physics of sound and waves. And today, we're going to unpack exactly how it all works.
So let's just jump right in with this question. On the surface, they seem like they're from different planets, right? One is this quiet little disturbance in water, and the other is just this massive blast of musical energy. But there is a fundamental link between them. So what is it?
The answer, it turns out, is beautifully simple. At their very core, they're both just waves. They are transfers of energy moving through something, whether that something is water, or air, or even a guitar string. And you know what? Understanding this one single idea is the key to unlocking pretty much everything else we're about to cover.
So, how exactly do we get from that simple ripple to a full-blown symphony? Well, here's our roadmap. We're going to start with the two basic kinds of waves. Then we'll learn how to speak their language, the anatomy of a wave. We'll use all that to finally understand sound itself, see what happens when waves collide, and then put it all together to uncover the physics behind the music we love.
Okay, first things first. Let's start with the two fundamental ways energy gets around. Believe it or not, every single wave in the universe, from light to sound, falls into one of these two categories. And the difference? It's all in the wiggle.
And here are those two flavors in action. A transverse wave kind of moves like a snake, you know? The wiggle is up and down, but the whole snake moves forward. A longitudinal wave, on the other hand, is a lot more like a slinky. The energy is a compression, a little squish, that travels all the way down its length.
So, the crucial point here, the thing you've got to remember, is the direction of that vibration. In a transverse wave, the little particles of whatever the wave is moving through, they move perpendicular, that's a 90-degree angle, to the direction the energy is actually traveling. But in a longitudinal wave, the particles just vibrate back and forth parallel to the direction of the wave. That right there, that's the key distinction.
Okay, so we've got our two types. But how do we actually describe them? How do we talk about them? To do that, we need to understand the blueprint of any wave. We need to learn its anatomy.
Turns out, every wave has four key properties. You've got amplitude, which is basically its power or height. Think a tiny little ripple versus a giant tsunami. Then there's wavelength, which is just the distance from one peak to the very next one. Frequency is how often those peaks pass by you in a second. And the period? That's just how much time it takes for one full wave to go by.
And this is such a clever way to visualize the difference. The image on the left is what we call a position picture. It's like taking a photograph, freezing the entire wave in one single instant. This is how you measure its wavelength. But the image on the right, that's a time picture. Here, we're just staring at one single point, and we're watching it move up and down over time. This lets us measure the period. Two different views, two different properties.
And get this, there's a really simple but super important idea here. Frequency and period. They're basically just opposites. If a wave is zipping by really fast, a high frequency, then the time it takes for one wave to pass is going to be super short, right? That's a short period. If it's slow, it takes a long time. They're just two sides of the same coin.
All right, we've got our wave toolkit. Now for the really cool part. Let's use it on something we experience constantly, but can't actually see, sound. This is where we make the invisible visible.
So how does a speaker actually make sound? Well, as that cone vibrates back and forth, it pushes on the air particles right in front of it. It squishes them together, creating these little areas of high pressure called compressions. Then when it pulls back, it creates areas of low pressure called rarefactions. And this push-pull, this series of squishes, creates a longitudinal wave that travels from that speaker, through the air, right to your ear.
Okay, so this leads to a huge aha moment. We always see sound drawn as that classic up and down wave, but we just said it's a longitudinal pressure wave. So what gives? Well, the y-axis of that graph, that up and down part, it just represents the change in air pressure. The peaks of the wave, that's high pressure, the compressions. And the troughs, the valleys of the wave, that's low pressure, the rarefactions. We're just graphing pressure.
And this is where all that physics stuff connects directly to what you and I actually hear. A wave's frequency directly determines the pitch. A really high frequency sounds like a high-pitched note. A wave's amplitude determines the volume. High amplitude, big wave, means a loud sound. It's really that direct of a link.
But in the real world, waves almost never travel alone. They're constantly meeting, mingling, and interfering with each other. So the big question is, what happens when waves collide?
This slide shows you exactly what can happen. When the peaks of two waves line up perfectly, they add up and they create an even bigger, more powerful wave. We call that constructive interference. But what if the peak of one wave lines up perfectly with the valley of another? Well, they can completely cancel each other out. And that's destructive interference. It's literally the science behind how your noise-canceling headphones work. And when two identical waves collide in just the right way, traveling in opposite directions, you get this absolutely beautiful phenomenon, a standing wave. It looks like it's just vibrating in place, not traveling at all. And these standing waves, are the entire reason a guitar string or a flute can make a clear, steady note. They are the absolute foundation of music.
Which brings us to our grand finale, where all these different ideas finally come together. We're talking about the sound of music. This is where we see how physics literally creates harmony. Just take a look at these two waveforms. On the left, you've got a pure tone, like what you'd get from a tuning fork. It's a simple, perfect, smooth sine wave. Now look at the right. That's a rich tone, like from a violin. See how it's complex and jagged and way more interesting? So what's actually going on here?
The answer is that a rich tone isn't just one wave. It's actually a main wave. That's the fundamental note, plus a whole cocktail of other, smaller waves, called overtones, all mixed together through interference. And that unique recipe of overtones is called its timbre. And it's why a violin and a piano sound so completely different, even when they're playing the exact same note.
Okay, one last huge concept for you, resonance. This is such a powerful idea. It's what happens when you apply a force to an object at just the right frequency, its own natural frequency, and that causes its vibration to get bigger and bigger and bigger. The classic example, pushing someone on a swing. If you time your pushes just right with the swing zone rhythm, they go flying much higher with very little effort. That's resonance.
And this tuning fork demonstration is the perfect way to see resonance in action. First, you strike one tuning fork. It starts creating sound waves at its own natural frequency. Now, those waves travel through the air as tiny little pushes of pressure. When those pushes hit a second, identical tuning fork nearby, they're arriving at exactly its favorite frequency. So the second fork absorbs that energy, and like magic, it starts to vibrate and sing, all on its own. So cool.
So, we've gone on this whole journey, from a simple wiggle all the way to the physics of a symphony. We've seen that sound isn't really a thing so much as it is a disturbance, a wave of pressure that needs something to travel through. Which leaves us with one final thought to ponder. If there's no air and space to carry those vibrations, can music, as we know it and as we feel it, even exist out there? Thanks for watching.